Hi everyone, my name is Tran. I'm an undergraduate student in the University of Texas at Arlington. Today I'll be discussing how fine-tuning lightweight models can enhance melanoma classifications. This work is aimed to improve early detection rate of melanoma, a deadly form type of skin cancer using AI techniques while balancing computational cost and performance. So we aim to discuss about the efficient models, why do we need them, the strategy in detecting melanoma skin cancer from dermoscopy images, and what are the current challenges so far. First of all, what is melanoma? Melanoma is a type of skin cancer that starts in the melanocyte, the cell in our skin that make melanin, the pigment that gives us the skin color. If this melanocyte is damaged through UV light, it can cause mutation in the DNA and they can grow out melanin out of control, which cause melanoma. These melanoma can go undetected until it reaches the dangerous stage, which significantly reduces the survival rate of patients having melanoma. A, a way to check if we're having melanoma is through routine checkup with our dermatologist, and they have to use special device to capture the pictures of the lesion image, the lesion part of our skin. They call them Cosby images. Here's all the example of it. They use it to examine the part during checkup, and while they having a good accuracy score, the dermatologists are highly skilled in identifying melanomas, right? But their analysis can sometimes vary due to human factors such as different levels of experience and subjective judgment. What AI can offer to help here is that they can provide a standardized way of examine lesson images through various data sets of images that they are learned from. And they can access these experts by offering a consistent objective second opinions for the probability of if someone is having melanoma or not. This can improve initial diagnosis and timely recommend patient for further testing, such as biopsy where we take a sample of the skin when needed. By integrating AI into this process, we aim to boost the survival rate for patients diagnosed with melanoma, catching potential life-threatening cancer earlier when they are most treatable. So why do we need to use the lightweight models? First of all, let's discuss how can AI model recognize all of the pattern of the melanomas. The most popular form of using image recognizer classification is through convolutional models, and EfficientNet is one of it. For image classification, we usually want to scale everything up. We want to scale the resolution using high resolution of the input image. We want to scale the depth. We want to have a lot of layers so then the images can learn all the patterns of it. It's really computational heavy. What EfficientNet did differently is that they combine off the scaling up into compound scaling. They offer a fixed ratio that is a learnable parameters during the training, so they will try out different scaling, balancing the performance and the accuracy score. So even though both traditional and efficient AI models might require similar computational resource, one strain, but there is a crucial difference that make efficient models preferably for deployment, especially in less equipped or resource-constrained settings. The main goal is to help them in every small clinical, and by using AI, we can increase the capacity of having patients going through all this routine checkup. So what we first pre-process of the demoscopy images to tensor. In 380 by 380 pixels, we used ISIC 2020 for training and validating as our dataset. 2020 ISIC is known for having only 5 or 10% of melanoma skin cancer in the entire dataset, which is crucial because our main goal is to use a small sample of dataset and then use it to see how well the model can perform on unseen data, and that's why we used a different dataset, ISIC 2019, for testing. So in a pre-processed approach, we scale the image, we shift the image, we change the brightness, we rotate it. The main goal is that we try to artificially increase the number of melanoma images in our dataset using just these type of augmentations. Furthermore, we also use the pre-trained layer of EfficientNet before, which has already been trained on a broad range of images and we want to specialize it for melanoma detection. Because of it, we're gonna remove the last layer, the fully connected layer that they use for classification, and we're gonna add three more of fully connected layer through a dropout, linear layer, and batch normalizations, so then we can scale off that back to a binary classification models, which is 1 for melanoma and 0 for non-melanoma. This process allows us to optimize performance without the cost of training a large model from scratch. So, what would the result? Using confusion matrix and ISIC 2019 for testing, we take a sample of 5,000 images from that dataset. These are the unseen data that has not been go through in the training phase or in the validating phase. And the results are really promising. We were able to gain an F1 score, an RAOC score of above 0.96. So we show that by fine-tuning these lightweight models, using them effectively, we can achieve similar accuracy to the heavier counterparts. This not only make AI-driven melanoma detection more accessible, but also more feasible with widespread clinical use. So in our scope, we aim to refine this method further to enhance the accuracy and efficiency. Thank you everyone for joining today to see the presentations. This project explored the applications of a fine-tuned efficient net B4 model for melanoma detections. Through this work, we demonstrate the power of lightweight models and identify complex patterns in medical imaging, especially in scenarios where computational resources are limited. These results showcase the effectiveness of transfer learning, fine-tuning, reusing existing architects for real-world medical applications. By doing so, we can now look toward deploying such models in clinics worldwide, significantly increasing the capacity of skin cancer screening, especially in low-resource or high-demand environments. However, in these projects, we only focus on binary classification, distinguishing between melanoma and non-melanoma. This highlight the need for further validation and extension to cover other types of skin cancers, and that will be crucial step for a global scale adaptations and ensuring broader impact across various healthcare systems. Thank you very much.